Good morning, everyone. It's very great pleasure indeed for me to be able to attend this workshop. I'm working with Professor Wei He in intelligent control for robot and human-robot interaction. Professor Wei He is my research team leader, and he recommends me to present my recent relative works in the workshop. I'm an associate professor in the Institute of Artificial Intelligence, University of Science and Technology, Beijing. I'm also a faculty in Research Center of Intelligent Control and Unmanned Systems. Today, I would like to present my work, Human-Robot Collaborative Carrying, using visual and force sensing. My presentation will cover the following aspects: introduction, research content, and the conclusion. We know that physical interaction of human and robot in shared environments and joint tasks pose many challenges. There exist extensive applications of physical human-robot interaction found in service and industrial areas, including assembly, rehabilitation, and so on. Co-carrying tasks, which rely on complementary advantages of human and robot, cannot be accomplished individually by a single human or robot. Considering many tasks that need at least two persons to complete, such as moving a table, one person finds difficulties due to limit of the maximum extension of human arm and human load ability, so it needs another person to cooperate with him or her. We can say limited by the weight of the medical equipment in handling tasks. Two nurses are needed to accomplish the task. Limited by the length of the structure in wounded transfer. Two first aid persons are needed to accomplish the task. Inspired by human co-carrying, robot is utilized to substitute the collaborative human and robot co-carrying can save manpower. Human co-carrying show better task adaptability compared with the robot and robot co-carrying when environment changes suddenly or task object changes. And robot co-carrying can save human efforts compared with human co-carrying. Human-robot co-carrying combines perception and decision-making ability of human with the load and movement ability of robot. It can used in unstructured environment and decrease number of human participants and human forces. In human-robot interaction, to ensure finishing the task successfully, the robot should perceive a precise ordered location and know prior task processes. But more than that, the movement of this robot should be compliant to the motion of human completely. It means that robot will need to know motion intention of human and adapt to movement and interaction force of human. There are two collaborative modes. One utilizes only force sensing. Human leads the task and the robot is blind to task and follow human passively. It will generate delays or counteraction. Another method is utilize force and visual sensing. Robot has a visual ability and follow human actively, and the motion synchronization can be achieved. In our work, the focus of interest is using vision and force sensing together to enable human and robot collaboratively to perform a co-carrying task. Coupled relationship between robot, transported object, and human bring difficulties in analyzing behaviors of both human and robot. Robot should have the following ability. The first is visual sensing, as measure human motion and estimate the human motion intention for achieve motion synchronization. And second is force sensing. It can measure the external force on robot gripper and regulate interaction force for achieve safe interaction. The third is interaction control. It carry out human in-the-loop control strategy considering system uncertainties. Also, we focus some key issues such as how to solve robust dynamics uncertainties and unknown disturbance. And second is difficult to mount on the force sensors limited by the practical application. The third is how to estimate human motion intention for achieve the cooperation. And the innovations are as follows. First is the observer is designed for estimating human control effort based on the knowledge of control input of robot and object dynamics. Thus, no force sensor is required on human side of the transported object. The second is human motion intention is estimated by minimizing estimated human control effort, and visual sensing is employed in obtaining human motion, which is used in observer. And human-in-loop impedance control strategy considering robotic dynamics uncertainties is proposed, in which neural networks are utilized to compensate for robot's dynamic uncertainties. Thus, accurate dynamic model of robot is not needed in torque control design. Research content contains four parts: system description, control design, and sensing, observer design and stability analysis, and experiment evaluation. And first, we will introduce a system description. We can see the MCG denotes a mass matrix, Coriolis centripetal matrix, gravity vector of the robot and object. In our work, we also propose a dynamic model of the object. We can see the states of the object changes due to the external forces of human and robot. It's a reductant control system. X0 denotes the position of the object's mass center. Xe denotes the human motion intention. Next, we analyze the control input of the human, where Kh denotes stiffness matrix of human and Xh denotes the human position. If robot knows the human motion intention Xe in real time and move towards the designed motion Xd according to Xe, the co-carrying task can be performed successfully and actively. If Fh, Xh, and Kh are obtained, Xe can be calculated. Before we design a tracking control algorithm for robot, some issues should be addressed about how to acquire Fh, Kh, and Xh. In a scenario where it's infeasible to directly measure human force, how we can obtain Fh should be considered. There are differences between Xh and Xr when human and robot collaborate to transport the object, so how we obtain Xh should be addressed. Without knowledge of human stiffness Kh, an effective estimation method to obtain Xe should be proposed. Next, we will introduce the control input of robot. Different from the definition of control input of human, control input of the robot is UR rather than the external force FR on the object. In view of the control objective, the control input of robot is designed as follows. We can see the URB denotes the feedback input for tracking the desired trajectory XD, and the URI denotes the input for compensating for the interaction force, and the URF denotes the feed-forward input for compensating for robust dynamics. We see the URB is just like a PD controller where it contains a proportional gain matrix and differential gain matrix, which can be interpreted as stiffness and damping matrix in impedance control. And URF, we can see that neural networks are employed to compensate for unknown robotics dynamics. The weight adaptation law is designed according to the backstamping method to estimate robotic dynamics. We can see if we set the XD as Xe, which means that the robot is aware of human motion intention, robot can conduct synchronous and active collaboration with human partner in the co-transporting task. If we want to update Xd relative to Xe, we need to obtain human motion Xh by visual sensing. In visual sensing, the calibration board is located on the board. And the position of human hand is approximately same as the position of a calibration board. We use a calibration board to obtain the board position, which we can obtain the human hand position. There exists another method. Human hand position is obtained by connected V2. Body basis D2D of connected DAMP's camera is utilized in obtaining position information of human hand. And we notice that in practical application, moving average filters should be utilized because the calibration board may be not recognized in the task. Filters can provide predicted data if detected signals are missing. XH obtained by the visual sensor should be transformed into the robot coordinate for further control design. Calibration systems are employed to obtain the relationship between the robot coordinate and the camera coordinate. So calibration board is fixed on the robots and effector. The transformation matrix RKT denotes the camera to the robot reference coordinate, and the matrix RET denotes the robots and effector coordinate with respect to robot reference coordinate. Matrix ECT denotes the calibration board coordinate with respect to robots and effector coordinate. And the matrix CKT denotes the camera coordinate with respect to calibration board coordinate. The transformation matrix RKT can be obtained as follows, which can be rewritten as this. Consider that ECT has no change when robot is in different poses. Transform coordinate matrix in two different poses are given as follows, where 1 and 2 denotes two different poses. Then we write it as follows. In particular, we use a well-known matrix to obtain RKT. By fixing the calibration board at a human hand position on the object, we can transform the human motion from the camera coordinate K to robot reference coordinate R. And about force sensing, we know the ATI Nano 17 calibrated force torque sensor is used to obtain 6 degrees of freedom forces and torques on the robot gripper. And in another way, a RobotEQ force torque sensor is used to obtain force and torque on the robot wrist. Moving average filters are designed to obtain smooth force data. Limited breadth filter is utilized to deal with disturbance from the external environment and mechanical friction. You can see a force sensor is mounted on the robot gripper, and the calibration system are utilized to obtain the relationship between the robot reference coordinate R and force sense coordinate F. The transformation matrix RFT denotes force sensor coordinate with respect to robot reference coordinate. Matrix EFT denotes force sensor coordinate with respect to robots and effector coordinate. And matrix RET denotes the robots and effector coordinate with respect to robot reference coordinate. So RFT can be transformed. Then we transform control input of human from force sensor coordinate F to robot reference coordinate. From the engineering point of view, it's infeasible to mount the force sensor on the human side of the transported object or on the human hand. We rewritten the object dynamics as state space form and design observer to obtain the human interaction force and design parameter updating law. For better illustrating control and observer design, a block diagram is given. Human motion intention XE can be estimated based on the control input of human, FH, and the control input of human has been estimated by our proposed observer, so XE can be estimated. We set the robot's designed trajectory XD based on the updating law, which means that the robot is estimating the human motion intention line, which means XD is generated towards XE. Although a human robot co-carrying task is studied as a specific application, the proposed framework can be extended to other scenarios of physical human-robot interaction that rely on force and visual sensing. such as human-robot collaborative assembly, teleoption, and sewing, and so on. We also analyze the system stability by defining the abnormal function handedness VE, considering the tracking error and the neural network weight error, and VK considering object position error and estimated stiffness error and estimated force error. Vx considering the human motion and human motion as a motion intention error. We can conclude that variables .e, fh, and tilde delta are bounded. We also do some simulations. We consider a scenario where human and robot perform co-transporting tasks in XY plane. The object is chosen as a 0.1 meters long board, which is located parallel to x-axis. In this task, rotation is not considered and any translational motion is involved. The human hand grasps one end of the board and the other end of the board is held by the robot gripper. The task objective is to move the object from an initial position to a target position. We consider the initial position vector of the robot gripper and the initial human hand position vector. We consider the robot as a simple two-link manipulator. We can see that under our proposed framework, the motion synchronization of human and robot can be achieved when the target positions are different. And also it illustrates the effectiveness of our proposed observer. As shown in the figures, the right arm of the Baxter robot is employed to cooperate with human to perform the co-transporting experiment task. Angles, angular velocity, and torques can be obtained by sensors in all 7 joints. Considering both accuracy and computational efficiency, 2 computers are utilized in experiment. One computer is used to calculate the feed-forward input by MATLAB Simulink and transform the compensation values to other computer by UDP communications. The other computer is used to receive sensory information from Baxter robot, visual sensor and force sensor, calculate feedback control input and generate control input to control the robot by ROS RSTK. And note that Jacobian matrix transpose can be obtained from Python. Kinematics and dynamics library and the control torque vector of 7 joints can be calculated. Kinect 2 3D depth camera is utilized as a visual sensor for obtaining human motion XH. And Kinect 2 contains a color camera, a depth sensor, and 4 microarrays and provide capabilities in 3-dimensional motion capture and voice recognition. It's mounted on the hand of the Baxter. Quick response detection method is applied in Kinect 2 to obtain the 3D position of the calibration board, which has been fixed on the human side of the board. We can obtain 3D location of human hand XH as a position of calibration board. Calibrated force torque sensor ATI Nano 17 is used to obtain the force and torques on the robot gripper. And the experiment has been performed with 4 subjects with age ranging from 20 to 32. The group is formed of 3 males and 1 female, all right-handed, who are from our university and they have robotic research experience but are blind to experiment settings. Human subjects and robot co-transport the object in the direction from the same initial position to the target position. Due to human motion uncertainties in real applications, we only ensure the similar XH of 4 subjects. This figure duplicates that the task can be accomplished by different human subjects, and the sensor noises and rotation around the x-axis result in non-smooth curves of xh and xr, which may influence experiment results and cannot be avoided. And this figure shows that the motion synchronization of robot of subject B can be achieved on y-axis and z-axis. Also, main A square error is employed to evaluate the robotics of our proposed method. We have added a criteria, motion smoothness, and defined it as a distance between the upper and lower envelopes of the robot motion curve. The results of MSE and MS for different subjects are shown in this table, which illustrates a small tracking error for all subjects and a smooth movement. This figure shows that the external forces on robot are smooth and the co-carrying process are stable. Limited by experimental equipment, FH cannot be measured directly in our experiment. The table shows that FH of 4 subjects are small and continuous under our proposed method. We also compared our proposed method with visual serving control and passive impedance control. And visual VS is utilized only with visual sensor to achieve motion tracking, and pHRI relies on sensory information from only force torque sensors to achieve complete interactive behavior. VS control method is redesigned to make robot track XD towards human motion XH directly rather than human motion intention. And the PD-based controller is employed for tracking. The co-transporting task cannot be performed successfully only by VS method because there exist rigid connections between human board and robot. Therefore, we consider the tracking performance under VS without co-carrying the board for comparison. And a figure shows a motion comparison after 10 seconds under different methods, and the board length is deducted from the XR on y-axis for better comparison in this figure. Seen from this figure, there exists a delay in robot motion when VS control is involved. A traditional pHRI control method is used for comparison too, which is widely used in co-carrying tasks. The desired impedance model of robot is designed as a damping stiffness model. Seen from the figure, the robot motion under pHRI is less smooth and even include isolations. Human subjects report that they found the interaction uncomfortable. We conclude from the table that under our proposed method, A is smaller than that under pHRI, which illustrates that human subjects cost less efforts in the task. From the table, we find that our proposed methods show better collaborative performance compared with VS and pHRI in the task. We also apply our proposed framework in the human-robot collaborative carrying task on a ball and board system. The robot under our proposed method can not only effectively cooperate with human to move the board to the target position, but also actively avoid the ball falling from the board during the carrying task. And radio basis function neural networks control is designed to ensure robot comply with the human motion, considering uncertain robotic dynamics. Visual serving control based on visual recognition and location is used to generate reference height and angle to adjust the position and posture of the board to keep the ball staying on the board. The proposed hybrid framework combines the complementary advantages of visual serve control and intermittent control and keeps the ball and the board system stable. And to prove the manipulator can prevent a ball from falling off with disturbance actively in the task, in first case, we cover the operator's eye. And hence, the operator cannot know the position of the ball and cannot actively adjust the board to prevent a ball from falling off. The two tasks can prove our proposed control method has such ability to prevent a ball from falling off with disturbance actively during the human-robot collaborative carrying task. In second case, the operator and the backed robot hold the ends of the board separately, and the operator move the board to a target position. Meanwhile, the manipulator should comply with the operator and hold the operator carry the board to the target position. There is a yellow ball on the board, and the robot should prevent a ball on the board from falling off during the carrying task by adjusting the board. The Kinect 2 camera can identify the ball and locate its center position in real time. Seen from the figure, the carrying process of human-robot collaborative carrying can be achieved. And to prove the universality of our proposed method, we invited 10 different operators to do the repeated task and recorded the error between the center of the board and the ball. Therefore, we conclude that the control method has universality in the human-robot collaborative carrying task towards different subjects. We also apply our proposed framework to other tasks, and an adaptive impedance control for physical human-robot interaction is put forward in the task space. Further, we design a complete human-robot interaction framework with visual and force sensing. By utilizing a switch function, the constraint program with unknown initial tracking conditions can be solved to improve the tracking performance. And the adaptive impedance control algorithm realize a safe interaction situation between human and robots and can achieve a good control effort in different motion states. And we can see from the video. First, we put the object on the first table, and then the humans hold the handle at the end of the object, and robots use a Kinect to obtain the position of the human hand. The robot controls the right arm to the other end of the object according to the position of the human hand and the length of the object and clamps the object. Then the human and the robot move the object to another table together. We also do some works in human motion intention estimation. Delays are commonly encountered in a leader-follower cooperative mode. Human-robot co-transporting is a typical leader-follower task where human plays a leader role and while robot is a follower. We propose a hybrid visual force framework considering such delays in human-robot co-transporting. A human hand motion prediction method connectively is proposed to make robot know human hand motion. Motion synchronization can be achieved if robot tracks a filter and predicts human hand motion. Compared experimental results show that our proposed framework is effective in such co-transporting tasks, and the motion synchronization can be achieved. Human subjects feel comfortable and easy to accomplish such tasks. And in future works, co-transporting tasks such as human-robot collaborative assembly, teleoption, sawing, and so on will be further designed to evaluate our proposed framework, and a more robust machine learning method will be investigated to localize the human hand by visual sensor without a calibration board. Force sensors will be mounted on the human side of the board for evaluating human interactive experience using objective measures. Human user studies with questionnaires and subjective measures will be also designed. Okay, it has been my pleasure to give my talk about human-robot collaborative carrying using visual and force sensing. Thank you very much for your listening. If you have any questions, I would be happy to answer it.